Welcome to another lesson of transparent physics, and in this one we're going to be sharing some solution samples for one-dimension kinematics problems featuring the Scooby Gang, as was introduced in an earlier video. And what we see before us is a very typical first-year physics kinematics problem. A 1986 Nissan Pulsar is driving at 40 miles an hour when it applies the brakes and comes to rest 2.75 seconds later. What is the car's acceleration and what is the car's displacement while braking? So again, right up our alley. We'll be able to talk about how to set this up, how to choose the equation, and how to solve it. And believe it or not, we are already making progress, because if you remember our QUIPS acronym, the QUIPS acronym gives us advice on how we go about solving a problem, and we have already read the question, and today we got chocolate, so can't complain about that. All right, let's underline some information. All right, don't get distracted. A lot of people underline like every number they see. This is a number, but it's not a measurement, not terribly useful for us. We do have 40 miles an hour. We have 2.75 seconds. We're looking for the car's acceleration, and we're looking for the car's displacement. So the car's acceleration is an unknown. The car's displacement is another unknown. It says the car is driving at 40 miles per hour. That to me implies that this is an initial velocity, and it applies the brakes, comes to rest 2.75 seconds later. That's our time. Now, we talked about the idea that when we are looking to solve a kinematics problem, we need 4 clues. Don't worry about part B. Part B is not solving yet. So the information we have here only seems to indicate 3 clues. We have 2 pieces of given information and 1 piece of information we're solving for. And hidden in the text is another piece of information. Again, it says it applies to the brakes and comes to rest. So coming to rest is a very classic way of saying, hey, by the way, this object stops. So this is going to be VF. And we have completed stage 2 of QUIPS. We have underlined the information. And while we were doing that, we also started identifying the information. Now, identifying the information isn't just pointing at it and saying, look, there's information. Identifying information is making sure you know what variable it goes with. So, if we draw a sketch, doesn't have to be fancy. And after that, chocolate. And what goes good with chocolate is a nice cup of tea. All right. So we have just a quick sketch, nothing fancy. We have a road. We have a 1986 Nissan Pulsar. It looks kind of like this, and a little angular like that, coming down like that. I don't know, could have been worse. All right, so it's driving, and then it comes to rest later. So driving at 40 miles an hour is VI. VF is 0 meters per second. And the time that the entire problem takes to occur is 2.75 seconds. And we are interested in the car's acceleration. I always indicate acceleration with a double-headed arrow. And going back to where we talked about acceleration and velocity, we know the car is slowing down. So things slow down when velocity and acceleration act in opposite directions with respect to each other. So I'm going to draw the acceleration acting in the opposite direction of the motion. If you listen very closely, you can hear my dog snoring in the background. And then we are interested in ultimately displacement. Displacement. Okay, and we are set up and ready to go. So we've identified all the information. We know what variables it goes along with, and we know what we're searching for. This is also a good time to stop and pause and say, are all the units going to work out? We know that we have seconds for time, meters per second for final velocity, and initial velocities in miles per hour. So miles per hour doesn't fit with all these other ones. So let's pause for a moment before we move on, and let's get 40 miles an hour converted properly. So I'm going to set this up. Maybe say on this one. Okay. So we got 40 miles an hour. Notice how I put miles per hour, hours on the bottom, so it doesn't get confusing when we set up where we're going to cancel stuff out. We can do this in 2 steps. And we're going to get miles out of here, get it to meters, and we're going to get hours out of here and get it to seconds. So if we take a look at how our units cancel out, miles cancel with miles. And what do we got here? How about you? And hours cancel with hours. And that leaves us with meters and seconds, which is what we're interested in getting in order to convert it to SI scales. And then we just need to know the informations. 1 mile is 1609 meters. I remember that by saying it's 4 squared, 3 squared. 4 squared, 3 squared, number of meters per mile. And then 1 hour is 3600 seconds. And we'll do a quick calculation. Get our value here. So when we do this conversion, the idea is that we are looking, we take anything on the top, multiply, anything on the bottom, we divide, ignore ones, and I get 17 points, let's say 17.9. 17.9 meters per second. Okay. And that is all of the initial information. So we have completed another of our stages in QUIPS. We have identified the information and assigned 2 variables and a sketch. Next up, we got to ponder our procedure. What formulas match up with this information? Looking at these equations, well, looking at the information, to start with, we know that our missing clue is D. At least for part A, we don't know D. We're not being asked to solve for D yet. That's very messy. So we don't know the displacement. We're not being asked to solve for the displacement in A. So we're interested in a formula that doesn't include D at all. We're not solving for it. We're not given it. Quickest way to identify the equation. The only equation that is missing D is going to be Shaggy. VF equals VI plus AT. And we have VI, VF, T, and A, so it matches up perfectly. So we're going to solve part A to begin with. We're going to need to do a little manipulation here. I always like to write the initial equation down first, then manipulate it, then plug in the values. All right, so we're going to get rid of VI. So VF minus VI equals AT. And we want to get A by itself, so we want to get rid of T. And if you are of good memory, you'll notice that this equation is just the definition for acceleration, change in velocity over change in time. So we take a look at it. We could have dropped off VF to start with because it's 0. So it's 0 meters per second minus 17.9 meters per second. Good thing we did that conversion when we did. Divided by 2.75 seconds. Okay, so we just take that, plug it in. So negative 17.9 divided by 2.75, and that's negative 6.51 meters per second squared. And again, a negative acceleration and a positive velocity mean the object's slowing down. So that's what we expect to see. So that is the answer to part A. Now, part B, we are interested in the displacement. Part B. We're solving for D in part B. Okay. And now we are actually in a very comfortable place because we know A and we have all the other information as well. So if we take a look at our sort of the big picture here, maybe not that big. We know VI, we know VF, we know T, now we know A, and we're looking for D. So at this point, really, it's whatever equation we want to use. We have just, you wouldn't write all these things out to begin with, but for our sake, we have D equals 1/2 VI plus VFT, Daphne. We have VF squared equals VI squared plus 2AD, Fred. And we have D equals VIT plus 1/2 AT squared. And that is Velma. So, looking at what we have, we know that VF is equal to 0. Since VF is equal to 0, again, this term drops out, this term drops out. There's nothing that drops out in Velma. Again, when we take a look at this, again, Daphne is a solid equation to choose here. She's it's the easiest of the three equations. There's no squares, and the manipulation is basically already done for us. So I would say this is pretty much a no-brainer. Let's go with Daphne on this one and solve it out. So D equals 1/2 17.9 meters per second and 2.75 seconds. So we multiply this out. And we take 0.5 times 17.9 times 2.75. And we get 24.6 meters. And that would be the distance that you travel once you apply the brakes. So that's the basic way we set it up. Let me add one more thing to this. Oh, you know what? I got so excited about this. We forgot our last steps. Did we ponder the procedures? Did we pick the equations? Did we manipulate them? Yes. And we solve for them. Now, I feel like maybe we should do a little more work now since I skipped those steps to earn that. So we're going to add a part C to the question. And the part C is going to read as follows. People's reaction times vary. But let's argue, for the sake of this problem, and again, the internet agrees with me on this depending on what site you look at. Let's add part C here. Okay, total distance travel while braking. So let's take a look at this now. So we're going to take our original picture, we're going to expand it out a little bit. So we have two steps. We'll call this part 1 and part 2. Now part 2 we already solved. So right here, the person applies brakes. And from that point on, when they apply the brakes, they have an acceleration of negative 6.51 meters per second squared. And we've solved all this out. We know this. We know the final velocity in this part is 0 meters per second. We'll call that now final velocity 2. The initial velocity right at braking was 17.9 meters per second. Now the first part is a constant velocity, because you may have seen that there is something you need to brake for. So way back here, you recognize that something's happening. But it takes you 2.3 seconds to react. So this is our, sometimes problems will call this the reaction distance. And this is the braking distance. And this will be a nice opportunity to get another equation in play here. So what we want to do is figure out how far they traveled during the reaction time before they start to brake. And again, this is important when you're driving. If you're paying attention, your reaction distance is going to be lower. If you're trying to text while you're driving, your reaction distance is going to be a lot longer because your reaction time is going to be slower. Your car doesn't care. When you press the brakes, you press the brakes. But reaction distance is up to you. So, what else do we know? Well, if it's moving at 17.9 meters per second right when you apply the brakes, during this whole phase, during the reaction distance, you're not accelerating at all. You're just going at the speed that you were. So we're going to call the acceleration during this phase 0 meters per second squared. There's no acceleration at all because you're just driving at your speed. You're like, what? And then you put on the brakes and then you stop. So during this whole time, your velocity doesn't change. So that means that VF equals VI equals 17.9 meters per second. Your speed's the same the whole time. Okay, and that's all. That's during phase one. So notice I have a subscript on a subscript. So that's not terribly unusual in introductory physics. You're not going to have all sorts of problems where you need to do that, but yeah, a subscript on a subscript happens. It's a boat on a boat. Okay, so we have identified the information. We've got our new sketch, and what we are interested in now is what equation can help us find D. And we'll call that D1 now because that's D during phase one. So we actually do have a lot of information again. And just to mix things up a little bit, I'll show you another equation that we can use here. And we'll choose Velma this time. Again, I'm not promising that Velma is the easiest equation to use, but we haven't used it yet. So let's give it a go. So, and let's not forget this time, now that I've identified the formula I want to use. No. So this is the Velma equation. Now, the equation itself is kind of complicated, but remember that the acceleration is 0. So if the acceleration is 0, I don't like to plug in values until after I manipulate the equation. But I do make one exception, and that's if the value is 0. If this value is 0, there's no reason to carry this term. 0 times anything is 0. Don't bring 1/2 t squared any further, because 0 times anything is 0. If I take the number of hours I've spent acting in Hollywood times $100 an hour, I will still have $0 because I have never worked as an actor in Hollywood. So that term disappears. Everything attached to it disappears. Don't hang out with zeros. You'll become a 0 too. And now our equation is just this. So D equals VIT. And that's a very simple equation. So that's 17.9 meters per second. Reaction time is 2.3 seconds. So during the time before you even apply the brakes, you are going to travel 41.2 meters. which is actually a lot further than you travel when you brake. So, just another application. A little bit of additional information. We saw that we can apply Velma. We can simplify Velma because there's no acceleration during the first part of the problem. And then we get this nice, straightforward equation for constant velocity. So that's probably a little longer than your typical one-dimensional kinematics problem is. And again, let me real quickly refresh. One dimension means we're just going, say, back or forth or up or down. We're not like projectile motion, arc, or anything like that, although we will get to that in time. And there you go. We had an opportunity to try out 3 of our 4 kinematics equations. We got some unit conversion in there, got a little bit of algebraic manipulation going on there. So this is a great, solid, introductory one-dimensional kinematics problem. And since we're done with the problem, you know what that means. It's my solution bar. So we have totally used quips all the way through. QUIPS. All right. Well, I hope this was useful to you. It's not that bad as long as you take your time, show your information, make a simple sketch, but put the information in it, label it correctly, identify the information, where it goes with the variables, and then picking the formulas is usually pretty straightforward from there on out. Thanks for spending time with us on this lesson. I hope things have been made a little clearer for you on this lesson of transparent physics.